Hello, and welcome to Module 6 of the Fundamentals of Petroleum Geology series. Today we're going to look at traps.
A trap is one of the essential requirements for hydrocarbon accumulation. When petroleum is generated from a source rock, it moves up through the permeable strata and is lost at the Earth's surface, unless it's trapped on its way up. Now, Leverson defined a trap as the place where oil and gas are barred from further movement. So we're going to examine the trap today in a three-part program.
In Unit 1, we'll get acquainted with the nomenclature, consider different ways of classification, and take a detailed look at structural traps. In Unit 2, we'll look at stratigraphic traps. And the last part, Unit 3, covers hydrodynamic and combination traps and discusses the role of diapirs.
Many terms are used to describe the various parameters of a trap. Let's get familiar with some using the anticlinal trap, the simplest type, as our reference.
The highest point of the trap is the crest, or culmination. The lowest point is the spill point. A trap may or may not be full to the spill point. The spill point lies on a horizontal contour, the spill plane. The vertical distance from the high point at the crest to the low point at the spill point is the closure. The productive reservoir is the pay, and its thickness is known as the gross pay. Now, this can vary from only 1 or 2 meters in Texas to several hundred in the North Sea and Middle East. Not all of the gross pay may be productive reservoir, and that's why we differentiate gross pay from net pay. Net pay refers only to the possibly productive reservoir. Careful mapping of the gross to net pay ratio across the field is essential in reservoir development.
A trap may contain oil, gas, or a combination of the two. The oil-water contact, OWC, is the deepest level of producible oil within an individual reservoir. It marks the interface between predominantly oil-saturated rocks and predominantly water-saturated rocks. Similarly, either the gas-oil contact, GOC, or the gas-water contact, GWC, is the lower level of the producible gas. It marks the interface between predominantly gas-saturated rocks and predominantly oil-saturated rocks, or water-saturated rocks, as the case may be.
The accurate evaluation of these surfaces is essential before the reserves of the field can be calculated, and the accurate establishment is one of the main objectives of well logging and testing.
Now, where oil and gas occur together in the same trap as separate liquid or gaseous phases, gas overlies the oil because of its lower density. Now, whether a trap contains oil, gas, or both depends on source rock chemistry and level of maturation, as well as the pressure and temperature of the reservoir itself.
Some oil fields have a mat of heavy tar present at the oil-water contact. The tar is often produced by degradation of the oil if bottom waters have moved beneath the oil-water contact. Tar mats cause considerable production problems because they prevent water from moving upwards and displacing the produced oil. Boundaries between oil, gas, and water may be sharp or transitional. An abrupt fluid contact indicates a permeable reservoir. Gradational contacts indicate low permeability with high capillary pressure.
Immediately beneath the hydrocarbons is the zone of bottom water. The zone of edge water is adjacent to the reservoir. Fluid contacts in a trap are generally planar, but are by no means always horizontal. Should a tilted fluid contact be present, its early recognition is essential for correct evaluation of reserves and for establishing efficient production procedures.
There are several ways in which a tilted fluid contact may occur. One of the most common is hydrodynamic flow of bottom waters. However, we'll discuss this later on when we look at hydrodynamic traps. Within the geographic limits of an oil or gas field, there may be one or more separate pools, each with its own fluid contact. Each individual pool may contain one or more pay zones. Now remember, the ratio between gross pay and net effective pay is important and is generally mapped from well data as the field is developed.
There are many different types of hydrocarbon traps, and they can be classified into 4 major types: structural, stratigraphic, hydrodynamic, and combination.
Structural traps are primarily due to post-depositional processes which modify the spatial configuration of the reservoir rock, mainly by folding and faulting. Stratigraphic traps are those whose geometry is due to changes in lithology. The lithological variations may be depositional, as in channels, reefs, and bars, or post-depositional, as where strata are truncated or where rock lithologies have been altered by diagenesis.
Hydrodynamic traps are where the downward movement of water has prevented the upward movement of oil. And combination traps combine two or more of the previously defined generic groups.
Let's consider each of these four types in more detail. As we just mentioned, a structural trap's geometry is due essentially to some post-depositional modification of the reservoir.
Fold traps can be divided into several types. Those due to compression caused by shortening of the crust, those due to differential compaction of sediment over an underlying feature, and those related to diapiric processes.
Let's now consider the first two types of fold traps. Since diapirs cause many types of traps, fold traps of this nature will be discussed along with other diapir-related traps under a separate unit later in this video. Anticlinal traps due to compression are most likely to be found in or near geosynclinal troughs. Now, these troughs are usually associated with active continental margins, where there is a net shortening of the Earth's crust. In California, the tertiary basins form a major hydrocarbon province, which contains compressional anticlinal traps.
Within this province are a number of fault-bounded troughs, infilled by thick regressive sequences in which organic-rich basinal muds are overlain by deep-sea sands and capped by younger continental beds. These have locally undergone tight compressive folding associated with the apparent transcurrent movement of the San Andreas fault system. Many oil and gas fields are also associated with faulting. This faulting occurs as normal, reverse, or strike slip.
The Wilmington oil field in the Los Angeles basin is a giant anticlinal trap. It's approximately 15 kilometers long and nearly 5 kilometers wide. The overall anticlinal shape of the field is shown by the structure contours on top of the main pay zone. Notice also the cross-cutting faults.
From this cross-section along the line AZ, you can see the broad arch of the anticline. The main reservoir occurs beneath the Pliocene unconformity in Miocene and Pliocene age deep-sea sands. In areas of still more intense structural deformation, the anticlines may be associated with thrust faulting. Traps may occur in anticlines above thrust planes and in reservoirs sealed beneath the thrust.
In Wyoming, the Painter Valley Reservoir is a fairly tight anticline beneath a thrust plane, which itself is involved in thrusting along its southeastern border. Let's take a look at this in cross-section along the line AZ. Notice how the anticline is overturned and its southeastern side is thrust out. The anticline occurs beneath a series of thrust slices that in turn occur beneath a major unconformity.
It's very difficult to find such fields. In the past, if such an accumulation were found, it was generally by chance. Not until the recent advances in seismic techniques was scientific location possible.
The contrasting compactional folds occur where crustal tension associated with rifting causes a sedimentary basin to form, the floor being commonly split into a mosaic of basement horsts and grabens. The initial phase of deposition fills this irregular topography. Anticlines may then occur in the sedimentary cover, which is draped over the structurally high-horsed blocks.
Here's how such anticlines develop by differential compaction of sediment. At the time of deposition, thickness of a given sedimentary unit is thinner over the crest of the underlying structural high. Compaction then takes place over the feature. Deep-seated recurrent fault movement may also enhance the structural closure. Carbonate sedimentation tends to be higher in shallow water over underlying structural highs, so that shoal and reefal facies may pass off structure into a thinner increment of basinal lime mud.
Similarly, sandbar or shoal sands may develop on the crest of structures and pass down the flank into deep water muds. And that's why reservoir quality often diminishes down the flank of such structures. In the North Sea, there are good examples of oil fields trapped in compactional anticlines where Paleocene deep sea sands are draped over deep-seated basement horsts. The Forties field is an example of a compactional anticline on the western side of the North Sea. Regional structure is a southeasterly plunging nose bounded to the northeast and southwest by faults.
From this north-south cross-section, you can see the anticline developed at the Paleocene level, where the reservoir sands are sealed by tertiary clays above. The anticline overlies a deep-seated horst of Middle Jurassic volcanics. Source rocks of Upper Jurassic age occur around the edge of this horst structure. Differential compaction and recurrent fault movement seem to have then controlled the structure throughout the Cretaceous and into the Tertiary.
So far, we've looked at differential compaction folds occurring over deep-seated horst blocks. The compaction folds may also occur over biohermal reefs and other deep-seated rigid features.
Let's now consider faults and fault-related traps. In many fields, faulting plays an indirect but essential role in entrapment. The problem is some faults seal and others don't.
Let's look at the tertiary rocks of Austria, where the Geiselberg field is located. A major fault, the Steinberg fault, which trends northeast-southwest, provides the trap for this field. The fault is downthrown to the southeast with impermeable metamorphosed tertiary flysch comprising the upthrown block, and younger tertiary unmetamorphosed sediment comprising the downthrown block. It's these younger sediments which contain an oil field with a small gas cap.
Now, there are two requirements for this trap to be valid. First, the rocks in the upthrown fault block adjacent to the downthrown reservoir rocks must be impermeable. Second, the Steinberg fault, which extends to the surface, must be a sealing fault. Otherwise, oil and gas would leak up the fault plane to the surface, and the trap wouldn't exist.
Pure fault traps, as found in the Geiselberg field, do exist, though there are many more fields trapped by a combination of faulting and other features. A particularly important group of traps is found associated with growth faults.
Growth faults typically form as down-to-basin faults, contemporaneous with deposition in areas characterized by rapidly prograding deltaic sedimentation. The additional sediment pile triggers the formation of a growth fault.
The throw of growth faults increases incrementally downwards, and there's a corresponding thickening of the stratigraphic section in the downthrown block. Characteristically, there is a downthrown reversal of regional dip as the beds slump into the fault plane, creating rollover anticlines. The dip reversal is often enhanced by antithetic faulting, downthrown and dipping in towards the major fault. The angle of the fault diminishes downwards and soles out, typically into high-pressure, low-density shale, or into a salt formation.
Hydrocarbons can be trapped in several situations in growth faults, as seen in this cross-section in the Niger Delta. There may be genuine fault traps, where sands are sealed up-dip by the main or antithetic fault. However, the principal trap for oil and gas is in the rollover anticlines down-thrown to the master fault.
Along the Texas Gulf Coast, one of the best-known areas of large-scale growth faulting is along the Vicksburg Fault Zone, often referred to as the Vicksburg Flexure. It extends as a uniquely narrow system of growth faulting for some 500 kilometers around the Gulf Coast of Texas. Additional paralleling zones of growth faulting are present basinward from the Vicksburg Fault Zone. This cross-section across the Vicksburg Fault Zone shows how the Vicksburg stratigraphic section of the Oligocene age thickens on the downthrown side of the fault. The maximum increase in sediment thickness across the fault is approximately 1,500 meters near the Mexican border. Characteristically, there's a local reversal of the easterly regional dip adjacent to the fault plane, with a series of rollover anticlines developed on its downthrown side. These anticlines provide traps for an estimated 3 billion barrels of recoverable oil and 20 trillion cubic feet of gas.
Growth faults are also common in the deltaic depositional provinces of southern Louisiana and Nigeria, where they provide traps for considerable oil and gas reserves.
This is a map of the Niger Delta. It shows that individual growth faults are seldom more than a few kilometers in length, with curved traces developing scalloped fault patterns.
Let's take a short break while you read sections 1 through 4 of the manual and do the exercises at the end.
Let's move on to the second major group, stratigraphic traps, those whose geometry is due to variations in lithology. These variations may be caused by the original deposition of the strata, as in the case of a bar, as we can see here, or a channel, or a reef. Alternatively, the change may be post-depositional, as in the case of a truncation trap, or can be due to diagenetic changes.
Stratigraphic traps are harder to locate than structural ones because they're not often revealed by reflection seismic surveys. Also, the processes which give rise to them are more complex. A broad classification of the various types can be made. However, classifying traps has its limitations because oil and gas fields are transitional between clearly defined types.
Using the scheme proposed by Rittenhouse, a major distinction can be made between stratigraphic traps that occur within normal, conformable sequences and those that are associated with unconformities. This distinction is rather arbitrary, since there are some types, such as channels, that can occur both at unconformities as well as away from them. First, we'll consider traps that occur within normal, conformable sequences.
A major distinction is made between traps due to deposition and those due to diagenesis. The depositional, or facies change traps, include channels, bars, and reefs. Let's look at channels. Many oil and gas fields occur trapped within channels of various types, ranging from fluvial through deltaic to deep sea channels.
Many good examples of channel stratigraphic traps occur in the Cretaceous basins along the eastern flanks of the Rocky Mountains, from Alberta down through Montana, Wyoming, through Colorado to New Mexico. Now, these channels occur both cut into a major pre-Cretaceous unconformity as well as within the Cretaceous strata.
This is the South Glenrock oil field in Wyoming. It contains oil trapped in both barrier bar and fluvial channel reservoirs. This channel has a width of some 1,500 meters and a maximum thickness of approximately 15 meters. It's been mapped for a distance of over 15 kilometers and can be clearly seen to meander. Its environment of deposition cannot be in doubt.
A cross-section of the field shows that the channel is only partially filled by sand and is partly clay-plugged. The SP curves on some of the well logs suggest upward fining point bar sequences, a characteristic of meandering channel deposits.
Now, the South Glenrock field illustrates two important points about channel stratigraphic traps. First, because of their limited aerial extent and thickness, these reservoirs will not act as hosts for giant accumulations. Secondly, only part of the channel is actually reservoir. The rest is plugged by clay. Now, the second type of depositional traps to consider are barrier bar sand traps. Marine barrier bars often make excellent reservoirs because of their clean, well-sorted texture.
Coalesced barrier sands may form blanket reservoirs within which oil may be structurally or stratigraphically trapped. Sometimes, however, isolated barrier bars may be totally enclosed in marine or lagoonal shales. These may then form shoestring stratigraphic traps elongated parallel to the paleo shoreline. Let's go to New Mexico, where the Bisty field is located. It is a classic barrier bar sand. The field is about 65 kilometers long and 7 kilometers wide. It consists of 3 stacked sandbars with an aggregate thickness of 15 meters. These are totally enclosed in the marine Mancos shale.
The SP log shows the typical upward coarsening grain size motif, which characterizes barrier bars. Traps, similar to the Bisty field, occur in many of the Rocky Mountain Cretaceous basins, from the Viking sands of Alberta in the north to the basin illustrated here in the south. The third type of depositional stratigraphic traps to consider are reefs, or carbonate buildups, which have a rigid, stony framework containing high primary porosity. Reefs grow as domal and elongated barrier features, and have long been recognized as one of the most important types of stratigraphic traps. Reefs are often later transgressed by organic-rich marine shales, which may act as source rocks, or the reefs may be covered by evaporites. The oil or gas is trapped stratigraphically within the reef with the shales or evaporites, providing an excellent seal.
In Alberta, Canada, the Devonian Age rainbow reefs in the Black Creek Basin provide an excellent example of reef traps. More than 70 individual reefs, each containing various amounts of oil and gas, were discovered within an area about 50 kilometers long and 35 kilometers across. Total reserves of these reefs are estimated in excess of 1.5 billion barrels of oil in place and 1 trillion cubic feet of gas. As shown in this cross-section, two basic geometric forms of reefing are present: the oval form of the pinnacle reef and the elliptical form of the atoll reef. The individual reefs are up to 15 square kilometers in dimension and up to 250 meters high in relief. At the end of the reefal growth, evaporite sediments infilled the basin. The evaporites completely covered the reefs, thereby providing an excellent seal for hydrocarbon entrapment. There is a wide range of net pays found in the rainbow reefs.
Some reefs are nearly full of oil and gas reserves, while others contain a very small column of oil or gas at the very crest of the reef. Porosities and permeabilities also differ greatly from reef to reef, as well as within individual reefs. Such changes are due to variations in lithofacies and diagenetic effects, and are typical features of reefal traps.
Now that we've examined depositional traps, let's take a look at diagenetic traps, the second group of stratigraphic traps occurring within normal, conformable sequences. Diagenetic traps are formed by the creation of secondary porosity in a non-reservoir rock by replacement, solution, or fracturing. The tight, unaltered rock forms the seal for the trap.
Here we see a diagenetic trap formed by replacement, whereby dolomitization of a pre-existing limestone deposit has resulted in the formation of secondary intercrystalline porosity. The development of solution porosity is commonly associated with carbonate rocks, but may involve sandstones as well. Fracturing can cause secondary porosity in any brittle rock, whether carbonate, sandstone, shale, igneous, or metamorphic rock. For a detailed explanation of secondary porosity development, you are invited to view Module 5 of this series.
In Texas, the Sprayberry Trend has a series of diagenetic traps with oil reserves of about 1 billion barrels within a producing fairway about 240 kilometers long and 80 kilometers wide. This structure map is contoured on the productive Sprayberry Formation, a 300-meter thick section of tight Middle Permian age shales, siltstones, and limestones. Notice that the areas of oil production shown in green have little relationship to structure. Production comes from areas of fracturing throughout the otherwise tight Sprayberry Formation.
The depositional and diagenetic stratigraphic traps that we've just considered occur in conformable sequences, but they can also occur at unconformities. Now let's take a look at the second major group of stratigraphic traps, those for which unconformities are essential.
Sometimes when unconformities bring together porous reservoirs and impermeable shales, the shales act as both source rock and seal. In addition to being held in pure stratigraphic traps, many of these reserves are held in structural and combination traps as well. Unconformity-related traps can be subdivided into those which occur above the unconformity and those beneath. Let's first look at those occurring above an unconformity.
Shallow marine or fluvial sands may unlap a planar unconformity. A stratigraphic trap can occur where such sands are overlain by shales and are underlain by impermeable rock, which provides a seat seal. Unlapping up-dip pinch-out sands such as these could occur as sheets or as discrete paleogeomorphic traps. Traps may occur where channels are cut into the unconformity or where sands are restricted within strike valleys, cut into alternating hard and soft structure. It's important to note that it's necessary to have closure along the strike of such a trap, not just up-dip, as shown here. Here we see closure provided by the intersection of a sandstone pinch-out with a structural nose.
The second group of traps associated with unconformities is truncation traps, which occur beneath unconformities.
It's generally overlying shales which provide a seal, and often the source as well for such traps. As with on-lap traps, closure is needed in both directions along the strike. This may be structural or stratigraphic, but for many truncation traps, it may be provided by the irregular topography of the unconformity itself. Here, a buried hill provides closure for a subcropping sandstone formation. Many truncation traps have had their reservoir quality enhanced by secondary solution porosity due to weathering.
In Texas, one of the best-known truncation traps in the world is the East Texas field, which contained over 3 billion barrels of recoverable oil. The trap is caused by the truncation of the Cretaceous Woodbine sand by the overlying impermeable Austin chalk. It has a length of some 60 to 70 kilometers and a width of nearly 10 kilometers. Notice the necessity for structural closure at the northeastern and southwestern ends of the field.
This is a good place to stop and read sections 5 and 6 in the manual and do the exercises at the end.
Well, now that we've looked at structural and stratigraphic traps, let's consider hydrodynamic ones.
In these traps, a downward movement of water prevents the upward movement of oil or gas.
Pure hydrodynamic traps are extremely rare, but a number of traps result from the combination of hydrodynamic forces and structure, or stratigraphy.
In this ideal hydrodynamic trap, permeable strata are dipping from left to right. There's a monoclinal flexure in the rocks. Notice that this has no genuine vertical closure. This oil could not be trapped in it in a normal situation. Groundwater, however, is moving down through the permeable strata and is preventing the upward escape of oil. This oil is trapped in the monoclinal flexure with a tilted oil-water contact. Pure hydrodynamic traps like this are very rare. There are, however, a number of fields with tilted oil-water contacts where entrapment is a combination of both structure and hydrodynamic forces. Hydrodynamic flow can generally be demonstrated by a study of reservoir pressures across a field. Obviously, it's extremely important to recognize a tilted oil-water contact when one is encountered.
Well, now that we've discussed the three basic trapping mechanisms, structural, stratigraphic, and hydrodynamic, let's consider those which are due to a combination of two or more of them. There are, of course, many, many ways in which combination traps can occur. So let's go offshore to Louisiana to look at a trap that is caused by a combination of structure and stratigraphy.
The structure contours show a rollover anticline developed to the south of a major growth fault. You can see the characteristic arcuate shape of the fault plane. The rollover anticline, however, is cross-cut by a channel. Oil with a gas cap only occurs within the channel. Thus, the trap is due to a combination of structure and stratigraphy.
Now that we've examined the various types of traps, let's look at the role of diapiers, a major mechanism for generating many types of traps.
Diapiers, or domes, are produced by the upward movement of less dense sediments, usually salt or overpressured clay.
Salt has a density of about 2.03 grams per cubic centimeter. Recently deposited clay and sand have densities less than this.
However, as most sediments are buried, they compact, losing porosity and gaining density. Ultimately, a burial depth is reached where sediments are denser than salt. Depending on a number of variables, this generally occurs between 800 and 1200 meters. When this situation is reached, the salt will tend to flow upwards to displace the dense overburden. As seen in salt domes of the North Sea, this movement may be triggered tectonically, and the resulting structure may show some alignment. In other cases, however, the salt movement is apparently initiated at random.
Movement of salt develops several structural shapes. Here, a deep-seated salt dome has developed. It has generated an anticline in the overlying sediment. Here is a piercement salt dome, which has actually pierced the overlying strata. And here is another more unusual case in which salt has actually penetrated right up to the Earth's surface. When it reaches the surface, there may be a solution collapse feature, or occasionally in arid areas, salt glaciers, such as those in Iran. There are many ways in which oil can be trapped, on or adjacent to salt domes. There may be simple anticlinal or domal traps over the crest of the salt dome. There also may be fault traps, pinch-out traps, truncation traps, or unconformity truncation traps.
Occasionally, anticlinal structures are developed between adjacent salt domes. These residual features are known as turtleback structures and result from salt withdrawal on their flanks.
Major oil and gas production from salt dome-related traps comes from the U.S. Gulf Coast, Iran, the Arabian Gulf, and the North Sea.
Diapiric mud structures, not just salt, may generate hydrocarbon traps. And sometimes diapirs of overpressured clay intrude the younger, denser cover, and just like salt domes, mud lumps may even reach the surface.
Let's look at the percentage of reservoirs that occur in different traps.
Giant oil fields are defined as those with over 500 million barrels of recoverable reserves. Anticlinal traps contain 75% of the world's known oil reserves in giant fields, faults barely 1%, and traps associated with salt domes 2%. Only 13% of the world's known oil occurs in giant fields of a stratigraphic nature, and some 9% in combination traps.
Keep in mind that these figures record the known reserves of oil, not the actual reserves that occur beneath the earth. They thus indicate man's ability to find oil.
It's easier to uncover anticlinal traps than any other types of traps. They may be mapped at the surface, or they can be detected seismically in the subsurface. Stratigraphic traps, on the other hand, are more difficult. Fewer can be picked off a seismic section.
Most require an integration of seismic, log, and real rock data with sophisticated geological concepts.
Now, at this point, do sections 7 through 9 of the manual.
No, that's wrong.
That is wrong?
Yeah, that's
What am I
wrong.
supposed to say?
It's read sections.
Do read,
Right.
what, are they going to do the manual?
Well,
Of
I
course
mean,
they're
there's
gonna read the
reading
manual.
and there's doing.
This program has been sponsored in part by the following companies: Agip, Aramco,